Hello everyone, this is a quick tutorial on how to use CloudCompare to create a canopy height model. I'll also show how we can create digital elevation models or digital terrain models as well as digital surface models from the point cloud. So what I will first do is load in a point cloud. So in this case we're going to use one that's included in the Santa Rosa scan but not the same coverage as the data provided in eClass. Just as a quick note, when you're importing, if you're dealing with a very large file, you can select this tiling option and it will tile the input file, in this case into a 4x4 grid, and it will subdivide that into, in this case, 16 different point clouds. So that makes data management a lot easier, and it can make your life a lot easier, especially if you're running on a slower computer or you're dealing with very large point clouds. So when you're importing this, you can apply the tiling and it will save those individual files, in this case 16 files, into a folder, and you have your output path here. Now we wouldn't be doing that in this case. We'll just be importing as normal. Oh, let me do that again. It's accidentally tiling and we don't want that to happen. So we'll go ahead and open that. I'll make sure tiling is not selected, and I will apply that to all. And once that loads in, what we'll have is a point cloud that I will then just clip. It's a little bit long for what we need to visualize everything, so I'll just give it a little clip to make it a little bit easier to see everything that's going on. Inclusive, and there we are. I'll get rid of that remainder, and we're left with this point cloud. Now in this point cloud we can see that there are some interesting elevation with the ground, and there's some bumpiness. There's definitely a little hill in this end, and we can also see the canopy. Now what we can do first is we want to create the digital terrain model, or the DTM. To do this, we can use an algorithm that essentially flips this upside down and lays a cloth over top of it. And depending on which points are in contact with that cloth, they will be classified as ground points. And this is known as a cloth simulator and can be found in plugins, CSF filter, or the cloth simulation filter. Now we're dealing with not a super steep slope. We aren't in a mountainous area, and it's also not a very flat area, so relief is fine for this setting. And then there are some advanced parameters. So for cloth resolution, I'm going to set it to 1 unit, which in this case for this point cloud is 1 meter. So each pixel within the cloth will be 1 by 1 meter. We'll set this to maximum of 500 iterations. We don't need to make any changes to that, but that just means how many times it can adjust before it finishes. Same as what we looked at with unsupervised and supervised classification. And we also have our threshold, which in this case is 0.5, or the same 95%. So we don't need to make any changes, and for more information, you can check these out on the side here. So once we're happy with our parameters, I'll click OK, and this will be very quick in calculating a mesh. And we can see this mesh in an aquamarine color, and you'll also notice that there's some ridges here. Now these most likely originate from the scan lines from the LiDAR sensor itself, but for what we're doing now, it's okay that they're in there. There are different software that are able to process point clouds better, but they tend to be paid, and we haven't looked at them, so we wouldn't be using them. We'll just be using CloudCompare today. So this is what our mesh looks like, and you'll notice that it created a ground points and an off ground points point clouds. So if we select the ground points, we can see these are all the points that are in contact with the mesh. So we can overlay the mesh again, so we can see where all the ground points are. We can also see where all the off-ground points are, which in this case are essentially vegetation. Now what we can do is we have our mesh, which is our digital terrain model, or DTM, and we want to compute the distance between each of these points with this mesh. So that way we can get the Z distance, or the height above the terrain. So to do this, we can select the mesh, and then what we can do here is once we have them selected, we can go to Tools, Distances, and Cloud Mesh Distance. So what this does is it allows us to compute the distance between each point and the mesh that's underneath it vertically. So we don't actually need to change any of the parameters here, just making sure that our mesh and our original point cloud is selected. So we can press the big red compute button. This will take just a couple seconds or a couple minutes depending on the size of your point cloud. And once it's done, we can see this nice colored point cloud. And this is colored not by the height above sea level or the relative height, but instead it's colored based on the scalar field we've created, which is the cloud to mesh signed distance. Now at this point, there are a couple things that we can do. To create the canopy or the digital surface model, we can click on this button, which is the point cloud to rasterize function, and we'll select a grid. In this case, I'll say it's 1 meter, so we get 130 by 134 meters, and I'll set it as the height grid values, or just the height, and I'll take it as a maximum value in the Z direction. And if I update this grid, we get this nice canopy or digital surface model. So this is what the surface looks like. Now, if we wanted instead to get the canopy height model, we can go to the C2M sign distance, and we see that there is a difference. Again, we're selecting the direction as Z and the cell height as the maximum, and we see that we produce the canopy height model. Now, this can be exported as a raster, where we can export the heights, and this can also be done with the digital surface model. Now, if we want to create an actual canopy height model point cloud, what we can do is make sure that, again, that original point cloud is selected, and then we go into Edit and Scalar Fields. Now, scalar fields are pretty similar to the fields within attribute tables, where they have different values for each point. And what we can do is we can set the scalar field as coordinates. And we'll make sure to deselect, and then select Z, press OK, and now it disappears, because now we've shifted everything to being so many meters above sea level, for example, 200 meters above sea level, and we've now shifted it to being 0 meters since it's all normalized. And what we can see is that it does a pretty good job of flattening things out. It does look like there was a bit of an error here, so we might have to play with some parameters within the mesh creation. However, the rest of the plot is quite flat on the bottom. So we have a canopy height model, which is a normalized visualization of the forest, where the blue here and the lowest points are at 0, whereas the higher points are, in this case, around 30 meters. So this is a very quick tutorial on creating this canopy height model. And again, you can do the same thing with the rasterizing, where you can select, okay, in this case, we're doing the height grid values since it is the canopy height model already. And we have this lovely raster that we can then output and manipulate in whichever GIS program you prefer. So thank you for watching, everyone. If you have any questions, please let me know. And I hope this tutorial is helpful for your final project. Good luck, everyone, and have a good day. Bye.